All right, let's talk about one of the biggest mysteries in the history of science, and we're going to do it with a little help from an apple and the moon. We're about to uncover the universal rulebook that controls, well, everything. So let's jump right in. To get our heads around everything, from how a planet orbits to how a baseball flies, we have to start with this. A question that seems almost too simple. But trust me, the answer to this one question stumped the greatest minds on Earth for literally thousands of years. And our story really kicks off way back with the ancient Greek philosopher Aristotle. I mean, for nearly 2,000 years, whatever this guy said about physics was basically considered the final word. End of story. So Aristotle's big idea was, well, he kind of split the universe in two. He'd look up at the heavens, the moon, the stars, and figure, okay, their natural thing is to move in these perfect circles. But down here on Earth, things like apples and rocks, their natural thing is to just fall straight down. Two different places, two completely different sets of rules. And you know what? You can't really blame him. It just feels right, doesn't it? It's pure common sense. I mean, you push a shopping cart, you stop pushing, it stops moving. You turn your car engine off, it eventually rolls to a halt. Our everyday life seems to scream at us. To keep something moving, you gotta keep pushing it. Well, what if that common sense was completely wrong? It took the incredible mind of Galileo to look at the exact same world and come to a conclusion that was the polar opposite. And this one idea? It was about to bring 2,000 years of physics crashing down. So how on earth did Galileo see something that everybody else had missed for centuries? He realized there was a hidden force messing with all our observations, a force that was fooling every single one of us. And this was it. This was the light bulb moment. Forces don't sustain motion, they change it. They speed things up, they slow them down, they make them turn. That car rolling to a stop, that's not its natural state. It's stopping because of a sneaky force we don't always think about, friction. Get rid of friction and things would just keep on going. And this thought experiment he came up with is just brilliant. Okay, so picture a ball on a U-shaped ramp. You let it go from one side, and it rolls up the other side to pretty much the same height you started from. Easy enough. Now, what if you make that other side a little less steep? Well, the ball has to travel a lot farther to try and get back to its original height. So Galileo thought, what if you make the other side perfectly, totally flat? The ball would never be able to reach its starting height, so it would just roll on and on and on forever. This radical idea from Galileo was the perfect setup for our next heavyweight, Isaac Newton. He's the guy who took these concepts and hammered them into universal laws that would literally define physics for centuries. Newton basically took Galileo's amazing insight and packaged it into his famous first law of motion. He once said, "If I have seen further, it is by standing on the shoulders of giants." And Galileo was definitely one of those giants. The law is super simple. Things just like to keep doing whatever they're already doing. And this tendency, this sort of physical stubbornness that objects have to resist changes in their motion, it's got a name: inertia. In fact, Newton's first law is often just called the law of inertia. So how do you measure inertia? It all comes down to mass. Something with very little mass, like a butterfly, has tiny inertia, super easy to change its motion. But something with a whole lot of mass, like a giant truck, that has enormous inertia. It takes a massive force to get it going and a massive force to get it to stop. And this whole relationship between force, mass, and how motion changes is all wrapped up neatly in Newton's second law, maybe the most famous equation in all of physics, F equals ma. It's like a recipe. If you want more acceleration, you just add more force. Or if you're dealing with more mass, you're going to get less acceleration from that same push. Simple as that. Okay, so we've got the rules of motion down. But here's where Newton makes an absolutely legendary leap. He looks up from the world around him, up to the heavens, and decides to apply these very same rules to the moon. It was finally time to connect the apple and the moon. So let's think about the moon again. We know from Newton's first law that an object wants to go in a straight line unless a force messes with it. But the moon, it's going in a circle. That's a constant change in direction. And a change in direction is a form of acceleration. So if the moon is accelerating, there has to be a force acting on it, pulling it inward. And what could be doing the pulling? Newton realized it had to be the Earth. Now, let's look at our apple. You hold it up, you let it go, and it does not stay put. It falls. It accelerates toward the ground. So, according to the laws we just talked about, a force must be pulling on it. And we have a name for that force: gravity. And here it is, the mind-blowing connection that changed humanity's view of the cosmos forever. The force pulling the apple to the ground and the force holding the moon in its orbit are the exact same force. The moon is literally constantly falling toward the Earth. It just has so much sideways speed that it keeps missing. It's trapped in a state of permanent freefall. This was the ultimate mic drop moment in the history of science. Newton totally demolished Aristotle's idea of two different rule books. Nope, there's only one universe, and it follows one set of laws. The physics that makes an apple drop from a tree is the exact same physics that holds entire galaxies together. His laws are universal. Now, all this talk about gravity and mass leads to a super common point of confusion. So let's take a quick second to untangle the difference between mass and weight. It's so easy to mix these up, but they are totally different things. Mass is how much stuff is in an object. That's its inertia. And that amount of stuff is the same no matter where you go in the universe. Weight, on the other hand, is just a measurement of how hard gravity is pulling on all that stuff. And since the pull of gravity can change depending on where you are, your weight can change too. Think of it like this. You could go to the moon and weigh a lot less, or float around in deep space and be effectively weightless. But your mass, the actual amount of you, hasn't changed one bit. So yeah, that interplanetary weight loss center, probably not the best business plan. Which brings us to Newton's grand finale, his law of universal gravitation. And this is just wild. It's not just the Earth pulling on the apple. The apple is also pulling on the Earth, and you are pulling on the Earth, and the Earth is pulling on you. Everything that has mass pulls on everything else that has mass. And that leaves us with one last pretty cool thought to chew on. Right now, as you're sitting there, your body is exerting a tiny gravitational pull on everything around you. Your computer, the chair you're in, even the distant stars. It's an incredibly weak force, but it is there. It's real. So, what are you attracting right now?